going to take the review document that I handed out first day and work from that. And I've highlighted a few things just to keep me from wandering. But if there's anything in here that we don't get to and you want to talk about, just stop me and we'll go to town on it. All right. So, I think this one works. A lot of these are memorization. Right? Speaking of which, have you started memorizing your symbols for the periodic table? Good, good. Because that's not something you can cram for. It takes a while for it to kind of soak in. Number 2. In which of the following pairs of properties are both properties chemical properties? What are we looking for when we're looking for a chemical property? Remember, properties are potential. What's possible? And then chemical properties imply the possibility of a change of identity of substances. Okay, so that's what we're looking for. Let's see. If something freezes at 10 degrees and is non-flammable, okay, there's the key. Both properties have to be chemical. Right? So A has one physical and one chemical. And we're talking about non-flammable. So A's not it. Do we have an E? No, just a D. Okay, so A's out. That's not working too good. How about decomposes at 500 degrees Celsius and reacts with bromine? Yeah, both of those are chemical properties. Right? And then for multiple choice questions, you look for the squirrely ones, like 2 of the above, none of the above, all of the above, those type of things. If you have any of those, then you may have to assess all the others just to answer the last ones. But if they're all unique answers, then once you find the answer, you can stop. Right? Mark your answer and move on. So the rest of them should be combinations of chemical and physical. Poor conductor of heat, reddish brown in color. That's a combination. Actually they're both physical for C. And has a low density and is very hard. Those are both physical. Right, so we found our answer. And I've selected these as representative. Right? So that doesn't mean you're supposed to ignore the rest of them. Okay. Something to talk about. Let's see. Now why didn't I mark those? We ought to look at some of these chemical symbols just to see if you're catching on. How about you know what? I should have marked more of these. I should have marked this one. Let's see, where's my tool? Highlighter. Let's mark that one. Oh, wrong color. Well, that'll do. How about this one? How about that one? Maybe I left them out because most of them are definitions. Let's take a look at 3 anyway. When a substance undergoes a chemical change, it is always true that it liquefies. That's a physical change. Changes from a solid to a gas. That's another physical change. Converted to a new kind of matter with a different composition. Yeah, that's the one. C. How about 4? The description, 2 substances present, 2 phases present, is correct for. What they mean by that is you can't tell the difference between one and the other, and the composition is uniform throughout if it's homogeneous. If there are 2 or more phases present, then it's a heterogeneous mixture. Think of mixing sand and water. Right? It looks like it's well mixed, and then once you stop, things start settling pretty quick. Okay, so A would be for a heterogeneous mixture. How about 6? Which of the following statements is correct? And they're all unique. So once we find the right answer, we can stop. Elements but not compounds are pure substances. Now, you can have pure substances, compounds. Yeah. Pure substances are those that cannot be, they have one type of substance, cannot be separated by physical means. Now, compounds can be separated by chemical means, but the compound is still a pure substance. Elements are pure substance. Compounds but not elements, that's A in reverse. How about C? Both elements and compounds are pure substances. They can be, yes. I think it should be worded that way. Both elements and compounds may be pure substances. So we can stop there. That takes care of 6. 7? How about an element? An element is a substance that can be broken down into simpler substances by physical means? No. The only way you can break an element down is in a nuclear reactor. B, cannot be broken down into simpler substances by physical means. Well, while that's partially true, it could be a compound, right, and not an element. So that's not a good definition. How about C, can be broken down into simpler substances by chemical means? No, can't break an element down by chemical means. Cannot be broken down into simpler substances by chemical or physical means. That's a better answer. And when you have choices like that, for multiple choice, pick the best answer. Right? One might look right, but if you read the rest of them, you might find a better one. That's just good practice for taking multiple choice tests. Okay. Let's see if you remember any of these guys. 10, 11, and 12. Uh, 10 says the most abundant element in the universe in the Earth's crust are respectively. So 1 in the universe and 1 in the crust. How about the universe? Hydrogen, right? Because all the stars are predominantly hydrogen. So that means B or D could be it. How about the second one? In the Earth's crust is not helium. No, must be oxygen. Yeah, so D was the correct answer. Where was helium first identified as an element? Did your textbook talk about that? Look at the name. What does helium mean? It comes from the Greek for sun. Helium was identified spectroscopically in the sun first, before we found it on Earth. And it's pretty scarce on Earth. It's not very common in the atmosphere because it's so light, right? It just rises to the top and goes out into space. We don't have enough gravity to hold it. So where do we get most of our helium? From natural gas, right? It's buried in the earth. So when natural gas comes out of the earth, you have to clean it up before you put it in the pipes and send it to the houses. So you take the water out of it, you take other impurities, solid impurities, you filter it, and you run it through an exchanger and remove the helium. And then helium used to be a strategic element. And there were lots of abandoned salt mines in Louisiana and southern Arkansas and Texas. And the government, this is because we were working at the time on balloons. And the enemy, Germany predominantly, needed helium for their big Zeppelins. So we considered it a strategic element, and we stored it in these salt mines. And we had we had locked the market, in fact, in the United States. So we said, you can't have any. So that's why the Hindenburg was filled with hydrogen instead of helium, because we wouldn't let them have any. And you know how that story ends. All right, number 11. In which of the following sequences of elements does each element have a 2-letter chemical symbol? All right, so A through D. A, B, C, and D. All right, for the first one, barium. Symbol for barium. B8. Right? Iron. Right? And nitrogen. There you go. So that's not it, because one of them has a single letter. How about selenium? I'm sorry? SE. Speak up. I'm hard of hearing. Nickel? Strontium. SR? Yeah. It's an alkaline earth, just below calcium. When we had walkthroughs in the lab, I used to work in a research lab, and we had school kids come walk through the lab, do demonstrations. I had this instrument that would that I used to identify elements and quantify elements in solutions. So I'd stick the tube in different solutions of elements, and it would come out the flame different colors. And they love strontium. Strontium comes out a hot pink. So I'd have to do that one several times. Let's see. Antimony. This is an oddball. The Latin stilbium. SB. Boron. Just B.
I think
I'm sorry?
I think you went to number 12.
Oh, I did. Sorry. Backing up. Silicon. Okay. Zinc. ZN. And hydrogen. There we go. Oh, 2 letters? Okay. We found our answer, didn't we? Let's keep going. How about iodine? Okay. Xenon. Did I have you do that one? I don't remember if I did or not. That's an easy one anyway. And titanium. Okay, so now we can found that one, now do 12. Okay, indium. Okay, carbon. And what's the next one? Silver? AG, argentum. And B, let's see, iodine. Okay. We're getting some repetition here, aren't we? This one has one letter chemical symbols. That's what we're looking for in this group. Tungsten. Where is tungsten? I don't know if I had you do this one. Tungsten. The Latin is wolfram. C. Antimony. We did that one before. Actually, I did that one because I was on the wrong one. Boron and nitrogen. And then D is nitrogen, germanium. I think it's GE. Yep. And bromine. There we go. So B is our answer again. Okay, we're down through 12. Now we're back on track. Which one of the following statements about atoms is incorrect? Okay, an atom is the smallest piece of an element that can exist and still have the properties of the element. Well, that one's true. B is a free, isolated atoms are rarely encountered in nature. That's also true. C, atoms may be decomposed using chemical change. No, that's false. And then the last one, only one kind of atom may be present in a homoatomic molecule. That's true. Homoatomic means one atom. What they mean is one element. All right. Let's see. Maybe we ought to look at 15 also. Which of the following pairings of chemical formulas and molecular descriptions is incorrect? So, lithium cyanide, is that triatomic? Yep, has 3 atoms. So we're looking for the incorrect one. KCl, potassium chloride, heteroatomic. Yep, 2 different types of elements. N2, homoatomic. Yep, 1 type of element. And the last one, silicon dioxide, diatomic. Diatomic. Now there are 3 atoms in there, aren't there? Yeah, 3 atoms. So D is false. N2 would be diatomic, right? 2 atoms. Yep. And remember the diatomic elements: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. All of those exist in nature as pairings of 2 atoms of the same element. Let me see. We'll go to 21. Which of the following is a property of both the liquid state and the solid state? All right, we have gas, liquid, solid. And then we have volume and shape for each one. Gas is indefinite volume, indefinite shape, right? Liquid is definite volume and indefinite shape. And solid is definite and definite. Right? So either, let's see, which of the following is a property of both liquid and solid? So we're looking at these 2 that have the same property. definite volume. Let's see. No correct response. Right. That's one where you have the squirrely ones at the end. You have to look at all of them. So we don't have any selection in there that says both. The one where they have the same property is definite volume. All right. 22. In which of the following pairs of properties are both properties physical? About the first one, melts at 73 and decomposes upon heating. No, that's physical, chemical. This one is physical and chemical. B is a good reflector of light and blue in color. Yeah, those are both physical, aren't they? No, wait a minute. Is a good, following pairs of properties are both properties physical properties. Yeah, B is right. Yeah, physical and physical. Yeah, yeah, because we got some squirrely ones down there. C has high density and is very hard. That's also physical. So D must be, I left off E. D must be more than one correct. That's it, right. More than one correct answer. Alrighty. Let's see. There's some repetition in there. It's kind of like those psychology tests they give you sometimes. They give you like 3 or 4. You'll notice as you go through, there may be 100, 200 questions, and you'll see lots of them are very similar. They word them differently, I guess, to weed out wrong answers. Well, not wrong answers, but inconsistent answers. Yeah. So think of that when you see these that look alike.
More trick questions than
I'm sorry?
They're more trick questions than they are.
Oh, in the psych test? Yeah. Which of the following statements concerning elemental abundances in Earth's crust is correct? Okay. How about the first one? One element accounts, well, we got some squirrely ones down there too. More than one and none. None and more than one. So we have to look at A, B, and C, all 3 of them. One element accounts for over 1/2 of all atoms present in the Earth's crust. Yeah, that's true. Which one is that? Oxygen. Huh? Yeah, oxygen. So that was true. How about B? Silicon and aluminum are the 2 most abundant elements in terms of atom percent. No.
No.
Oxygen is. Still, yeah. So that one's false. And C, elemental abundances in Earth's crust closely parallel elemental abundances in the universe as a whole. No, because the most abundant in the universe is hydrogen. And while we have a considerable amount of hydrogen on the Earth, it's not the most abundant one. Right? Why do we have a lot of hydrogen on the Earth? Water. Right, H2O. In terms of atoms, numbers of atoms, not mass, because hydrogen doesn't weigh that much. Okay, so we got just this one. That's it. Okay, let's see. What about 33? Which of the following pairings of terms or concepts is correct? So we got another squirrely one's at the end. So this is more than one, and this is none, right? Okay. Okay, which of the following pairings of terms concept is correct? Atom, the limit of physical subdivision. The limit of physical subdivision. You know, that there might be a problem with that question. Right? If you keep dividing something physically, like separate this group of atoms, and you keep dividing, you get down to one, that's an atom. That is the limit of physical subdivision, isn't it?
Where did we go?
Yeah. Okay, so there's something wrong with that answer, because that one's correct. Molecule, limit of chemical subdivision. All right, if we're going to be picky about it, the limit of physical subdivision could be a compound, right? Because once you get down to the compound, you can't separate it anymore until you use chemical means. All right, so this one technically is not correct. It could be an atom, or if it's a pure element, or it could be a compound. It's stump the band time. Molecule, limit of chemical subdivision. No. Actually, the atom is the limit of chemical subdivision. So this one is also false. How about C? Compound, homoatomic molecule.
False.
No. Compounds are always composed of two or more elements. Yep. All right, so
Definitely D, so it has to be E.
E, uh-huh. All right, 34. In which of the following pairs of chemical formulas do both members of the pair have the same number of atoms per molecule? All right. So we have A, B, C, and then the squirrely ones. More and none. At least they're consistent. Okay. Sodium thiocyanate has 1, 2, 3, 4. 4 atoms in that molecule. So 4 versus, what's the second one? 1, 2, 3, 6. Yeah, 6. 2 hydrogens, 1 carbon, and 3 oxygens. So that's 6. So that's not it. Cobalt 2 chloride. 3, yes. Versus 1, 1, 2, 3, 4. Right. And then O2N2 is 4, right? And yeah, and 4. There it is.
BC.
We found it. Okay. Now these right here that start with, say, number 36, what you have to do is, I left those out because I didn't think we'd have enough time to do them, because they do take a lot of time. You look at the statement and you say, all 3 are true, 2 of the 3 are true, only 1 of the statements is true, or none are true. That's your selections, A, B, C, and D. So you have to look at each of those 3 statements and see which fits the truth test. So that's why I skipped all those. Okay, 46. For the elements, calcium, iron, and beryllium, choose the appropriate characterization of the set's chemical symbols from the response. 1 letter, 2 letters, all have 1 letters, all have 2 letters, all start with the same. Okay. So let's see what we got. Beryllium, calcium, iron, and beryllium. Calcium, iron, and beryllium. So what do those have in common? They don't have the same first letter. They have 2 letters each. All symbols have 2 letters. So B would be the answer. 47. Silver, sodium, and potassium. We did this one before. Silver, sodium, and potassium. K. Okay, they don't have the same first letters. 2 have 2 letters and 1 has 1 letter. So let's see. All symbols start with a letter which is not the first letter of the element's English name. That's right. They're all derived from the Latin. (48) Iodine, fluorine, and nitrogen. Right? Fluorine, all single letters. Right? 49. Gold, lead, and bromine. Y'all ought to know gold because that's got to be your favorite element. Right, AU. AU. AG is the poor man's gold. Silver. Right. What's silver now? It's about $45 an ounce, something like that. And gold is like, I don't know, 2,800. It's pretty high. I go for silver. So we got gold, lead, and bromine. All have 2 letter symbols. Yep. That's why the answer is B. How about 50? Let's see, I need to make some room here. Oops. For the element silicon, sulfur, and tin. We did silicon earlier. How about sulfur? And tin. Derived from the Latin. I'm sorry? Yeah. It's a weird one. From the Latin stannum. Right? That's why if you look at, sometimes I think even labels on toothpaste tubes will have added stannous fluoride. That's the way we used to say it in the old days. Stannous instead of tin fluoride. They all start with the same letter. Let's see, 54. Maybe that's why I skipped those earlier ones, because that one looks familiar. 54. Give the classification of matter when 2 substances exist with 2 phases present and the substances cannot be decomposed by chemical means. Well, when 2 substances exist in 2 phases, that's a heterogeneous mixture. But we qualify that with substances cannot be decomposed by chemical means. They have to be elements. So you have a heterogeneous mixture of two elements. So the best answer is elements. I think that's the idea behind that one is, well, the same as all word problems that confuse, just to see if you really know. So you look at both parts of that question and see which one satisfies both parts. '58. A substance is composed of diatomic molecules. Okay, choose the appropriate classification from the response list below. Composed of diatomic molecules. Could be an element or a compound. Yeah. For all you need is one example. Right? That's diatomic. That's diatomic. Right? Both will kill you. This one just takes a little longer. Carbon monoxide will knock you down, quick, fast, and in a hurry.
You don't even know it's happening.
I'm sorry?
You wouldn't even know it's happening.
Yeah. You know how it works? You know the physiology of carbon monoxide? It substitutes on hemoglobin for oxygen. Oxygen is usually picked up by the iron in your hemoglobin, carried to the cells, dumped, and then goes back for another load. Carbon monoxide replaces oxygen, only when it gets to the cells, it doesn't dump. It's attached to iron really strong. The bond is strong. So it won't turn loose and it won't let oxygen be carried either. So what you do is you suffocate at the cellular level. Nice thought, huh? Okay. Whereas nitrogen kills you simply by displacing the oxygen. Right? So you don't want to get in a closed room with lots of nitrogen around. Let's see, that was 58. We're going to skip a few and get down to 66. Which of the following substances is both homoatomic and tetraatomic? So homoatomic means single element. Tetraatomic means four atoms in the formula. Right? So which one has only one type of atom? C, right? P4, it's also tetraatomic. See? Which of the following substances is both heteroatomic and triatomic? So it has to have more than one element in the formula, and it has to have 3 atoms. Yeah, A is the only one that fits, because the others have, let's see, 4. Well, C doesn't make it because it's not heteroatomic, and then D has 6. Right, so A has to be the answer. Alrighty, moving on. Finally, chapter 2. The numbers are sequential, so I didn't have to write chapter 1, chapter 2, chapter 3. So we're going to pick up 71 here. Doing on time. Okay, we're doing good on time. Before I get into chapter 2, I want to finish handing these guys out. Is Akers here? Nope. Klein? Nope. Evans? Let's see. David? Yeah. What's their last name? Marcos. Okay. You're right, smaller than I did. McDonald? No. Mullins. Okay. Now we can go to chapter 2. The mathematical meaning associated with the metric system prefixes. Okay. Centi, milli, and micro. Centi, milli, and micro. How do these modify the base unit? That's what we're saying. If it's centi in front of the base unit, we're saying the size of the unit has to be reduced by 10 to the minus 2. 1/100th of. If it's milli, we're reducing the size of the unit by 1,000. Okay. If it's micro, we're reducing the size of the unit by 1,000,000. So, minus 2, minus 3, minus 6 is B. What are some others while we're here? How about 10 to the minus 1? Deci. Let's see. How about 10 to the minus 9th? Once you get down here, we start going in steps of 3s. Down here, nano. Okay. All right, that's good enough. Why do we even need those? Convenience. If you're measuring something really, 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 really small, the unit nano might be more convenient because the number associated then would be like in the more manageable range. 72. This one's starting to give out on me too. In which of the following sequences are metric system prefixes listed in order of decreasing size? Okay, let's see what we've got here. Kilo, giga, mega. I'm just going to list what we're given. Kilo, giga, mega, and then we got milli, nano, micro. Micro. And then we got mega, kilo, micro. Mega, kilo, micro. Got those already. And then pico, and kilo and deci. Okay. So this one is, right, 10 to the minus 1. Just did that one. Pico, we didn't get to that one. That's the one below nano. Pico is 10 to the minus 12. Kilo is 1,000 times bigger. Giga is 1,000,000 times bigger. No, giga's a billion times bigger, excuse me. 9. Mega is a million times bigger. Milli is minus 3, minus 9, minus 6. Okay, so we got to find, first one says kilo, giga, mega. And it has to be in order in decreasing size. So, no, it goes from this one to a bigger one. So, A's out. How about milli, nano, micro? Milli, nano, nope. It flips these two. Got to get smaller. Right? Okay. Mega, kilo, micro. Mega, kilo smaller, and micro smaller still. C is a good one. Yeah. So you can assume that the last one's wrong. we found the right answer. So the point of that question is to see if you know the definition for each one of those values. Which of the following is an incorrect pairing of terminology? Let's see. Kilogram, metric unit of mass. Yep, that's the fundamental unit of mass. Milliliter, metric unit of volume. Yeah, it's not the fundamental, but it is a metric unit of volume. Yep, milliliter. Meter, metric unit of length. Yep, that's the fundamental for length. And D, cubic centimeter, metric unit of length. Cubic cent, that's a volume, right? Yeah. What's a cubic centimeter equal to? A milliliter. They're exactly the same size. Cubic centimeter, milliliter, no difference. Let's see, 76. Do they still use cc's in the hospital? Maybe some old timers, they call for so many cc's of this and that. But I think the modern printed measurement on syringes and devices is milliliter. In which of the following pairs of measured numbers does each member of the pair contain the same number of significant figures? D. Stopped at D. Okay, how many significant figures in A? 3 in the first one, 4 in the second one. Right? The zero rule. The zeros to the right are significant if there's an explicit decimal. And there is. So we got 3 and 4. How about B? So that's not it. 4 and 1. Yeah, 80. The only significant digit in that number, 80, is 1, is 8. Because there's no decimal. Yep. How about C? Now, all decimals to the left are never significant. So the first one is 4, right? Versus 1, 2, 3. Okay? And the last one, 2 versus 2. There's no explicit decimal in 960,000, so it's only got 2 significant figures. And the first one, only 2 significant figures because all the zeros are to the left. $79. The measurement 8310.9. 8310.9 expressed in scientific notation becomes. What are the rules for scientific notation? The coefficient must be between 1 and 10. So we have to move the decimal 1, 2, 3 places. 8.3109 times 10 to the what? 3. If the coefficient gets smaller, we store positive values of positive powers of 10. If the coefficient gets bigger, we have to move to the right. And that stores up negative values in powers of 10. Okay, so D would be the correct answer for this one. calculator answer obtained from multiplying the measurements 64.49, 6.57, 423.70. Multiplying all three of those together, given the operational rules, this answer, measurement. Oh, the answer given is 423.70 in, let's see, in the calculator. Okay, is that correct? This has 5 significant digits, right? Do we have 5 significant digits in either of the multipliers? No, we got 4 and 3. So that's an incorrect answer. Should be rounded to, right here, correct? 423.7.
You always use the number.
Oh, wait a minute. I'm sorry, 3. My mistake. We only get 3 significant figures. So now we say, all right, here, 424. Does that answer your question? Once I do it right. All right, let's see. How about this one? 84. According to dimensional analysis, which of the following is the correct setup for the problem? How many milligrams are there in 85 kilograms? 85 kilograms, and we want to end up with milligrams. Okay. They're taking it in 2 steps. So I would assume that the first step would be get rid of the kilograms and change it to something else, probably grams. So we would either have 1 here and here like that, more than likely, and then change the grams to milligrams. So milligrams on top and grams on the bottom. This would be 10 to the 3rd and 1. So let's see. Does anyone match that, or do we have to flip it around a little bit? Because the other possibility is it could be 1 gram and 10 to the minus 3 kilograms. Or this could be 1 milligram and 10 to the minus 3 grams. That's another way of expressing it. It's exactly the same effect. So, let's see. Let's look at grams, kilograms, milligrams, grams. Okay, the first one's out because it's got milligrams on top and bottom. Then grams, kilograms. Second one's out for the same reason. C is bad because it's milligrams to kilograms. And this is the wrong ratio anyway. So the only one left is 1 gram or 10 to the minus 3rd. Wait a minute.
It says the answer would be
There's a typo. Isn't there? Yeah, there's a typo right here. Right there. That should be G. Excuse me. The bottom one should be G. Right? That's wrong. There's no right answer there. We expect B to be the right answer only if that milligram is actually grams. Okay? I'm glad we looked at that one because that's wrong. 84. I'll make a note. Fix it. Okay. This should be grams. I'll leave it highlighted. That'll also show it off. 87. I think I need, let me see if these guys are working better now. They've been upside down for a while. If object A weighs 6 grams and has a volume of 6 milliliters, and object B has 9 grams and a volume of 2.25 milliliters, and compare their densities. Okay, so the first one for A, the density of A is mass per unit volume. So are they both grams and milliliters? Yes. So we're comparing apples and apples. 6 grams per, let's see, 3 milliliters. Let's see there, 3 milliliters. That would be 2.0 grams per milliliter. How about B? 9 and 2.25. 9 grams and 2.25 milliliters. I need my calculator for that one. Sometimes I can do these in my head and sometimes I can't. Oops. There we go. This is 4 grams per milliliter. Okay, so the density of A is less than the density of B, or density of B is greater than A. B is twice as dense as A. Yep. That's why C is the best answer. '89. Which of the following comparisons of the size of a degree on the major temperature scales is correct? So we're talking about when you move from 1 degree Celsius versus 1 degree Fahrenheit versus 1 degree Kelvin, how do those size of those degrees compare? So look at it this way. If we've got a Fahrenheit thermometer next to a Celsius thermometer, and if we're only comparing size of degrees, then if we can find out the size of the Celsius degree, it's exactly the same as the Kelvin. So, freezing point here is 0. Boiling point is 100. Freezing point here is 32. Boiling point here is 212. So we moved, how far did we go from here to here? 190 degrees. No, 180 degrees. So this distance is 180 degrees Fahrenheit. Yep. This distance is 100 degrees Celsius. So if we're going from here to here, the same place compared to the same physical phenomenon, it only takes 100 degrees to go from here to here. It takes 180 to go. Which one's the biggest? The size of the degree mark. Right? If it only takes 100 of them, it takes 180 over here, so you got to have more of them to get there. Right? So the size of the Celsius degree is bigger than the size of the Fahrenheit degree. And the ratio is 9/5. Or 1.8. Right? So if you ratio 180 to 10, that's where you get your 1.8. All right, now let's answer the question. A Kelvin degree is larger than a Celsius degree. They're exactly the same. Fahrenheit degree and a Celsius degree are equal in size. Nope. A Fahrenheit degree is larger than a Kelvin degree. No, it's smaller. A Celsius degree and a Kelvin degree are equal in size. That's true. Now, if I got sneaky and offered this type of question on an exam and said something like, instead of a Celsius degree equal to a Kelvin, I said a Celsius degree is larger than a Fahrenheit degree, then that would be the answer. But since we worked it out here first, then it's easy to pick out the right answer. All right, 92. That was starting to get weak too. Let's grab another one. In which of the following pairs of units is the first listed unit 1,000 times larger than the second? Okay, so A, B, C, D, and E. We want 1,000 times larger. The first is 1,000 times larger than the second one. Okay. Milligram and nanogram. Well, a milligram is 10 to the minus third grams, and a nanogram is 10 to the minus ninth. What's the difference here? Is 6. We've moved up 6 powers of 10. Actually, it's not larger than. Sorry. So we can throw that one out. It's smaller than. So we don't even have to look at it. Let's see. A liter and a centiliter. A liter and a centiliter. So what's a centiliter? It's 10 to the minus 2 liters. So we're getting smaller again. Let's see. Kilometer and megameter. Kilometer and megameter. A big M is mega, a little m is milli. So we are getting bigger here. This is 10 to the third meters. This is 10 to the sixth meters. Right? 1,000,000 meters. So we did increase by 1,000. Okay. Wait a minute. Kilometer and mega. Oh, no, I'm going backwards. And that's why you got puzzled looks on your faces, isn't it? It's this one's larger than that one. So this one is, no, this one's a 1,000,000 times larger. This one is 100 times larger. That one doesn't work either. All right, so none of them. Right? There's no correct response. If I read the question correctly, right? What's the first rule? What's the question, right? You can't answer the question if you don't know what it is. I'd like to say I did that on purpose, but I claim old age. Ooh, that one doesn't want to come off. Ooh, we're not going to use that one anymore. '93. In which of the following sequences of measured numbers do all members of the sequence contain 3 significant figures? All right. A, B, and C, and then D and E are squirrely ones. So we'll get to those in a minute. So we're looking for 3 significant figures. So A has 3, 3, and 2, right? No arguments. Okay, we'll move to the next one. The next one has 2, 3, and 2. The last one only has 2 because there's no decimal. And C, let's see, 30.0 is 3. 0.300 is 3. And 30,100 is 3. There it is. $95. Which of the following statements concerning the measured number 0.3030 is correct? Only one of the zeros in the number is significant. No. This one's significant because of that. This one's significant because of those two. So it has, both zeros are significant. B, rounded off to 2 significant figures, the number becomes 1, 2. Yep. That's correct. B. What about C? Expressed in scientific notation, the number is 1, 2, 3. 3030 times 10 to the minus 3 because we moved to the right. Oops, sorry. That's dumb. I only needed to move once, right? There. All right, so there's no answer for that one. B is the best answer. $97. That was given out. Which of the following measured numbers contain 3 significant figures and has a magnitude of less than 1? 3 significant figures and it's less than 1. Well, A can't be it because it's greater than 1. Right. B is less than 1 and C is less than 1, and they both have 3 significant figures. Yeah. So more than 1 the correct answer. $99. Bet that one's going to be hard to get off. Which of the following measured numbers has an uncertainty of 0.01 associated with it? So 0.01 would be, the hundredths place would be the last digit. Right? 0.01. So we have to write those numbers in standard notation in order to pick them out. The first one, 32.930 is already in standard notation. Right? Its uncertainty is in the thousandths place. Right? So that's not it. B is 302 times 10 to the 6th. 302, let's see, that's 2, 3, 4, 5, 6. Right? Its uncertainty would be in that position. How about 3.0 times 10 to the minus 1? Move the decimal to the left 1. So 0.30, and keep that one. Actually, the uncertainty for this one is in the 1, 2, 3, 4, see, ones, tens, hundreds, thousands, 10,000s would be in the 10,000th position because those are not significant. And this one, yeah, it's in the 0.01 position. That's it. Yep. Okay, this one's not good. That was 99. Now we're in the centuries. 102. Density can be used as a conversion factor to convert from. If density is mass per unit volume, you can use mass per volume as a conversion factor. You can use mass per density as a conversion factor. I think that's it. Conversion factors are quotients. So A is mass to volume. We can go from mass to volume. If we want to go from mass to volume, what do we need? We need mass on the bottom, volume on the top. Well, that works. Yeah. So A is correct. How about B? Volume to mass. Yeah, you can do volume to mass. If you can do mass to volume, you can do volume to mass because all you have to do is just flip it, right? Conversion factors are all equal to what? 1. So you can flip them. Metric unit mass to English unit? Nope. So we do have more than one correct response. A and B. Did I lose anybody on that? Or am I just boring you? If you've got all this stuff down pat,
We were close.
it's a good sign. If you get bored with all this stuff, that's a good sign. It means you know what you're doing.
I'm still at the door trying to get in to learn it.
Oh, okay. Let's see. 103. I don't like this one either. Let's try a different one. The density of table sugar is 1.59 grams per mil. That's density. It is true that 2 grams of table sugar occupies a volume of 1.17. Okay. This is going to be a case where we have to set up Henry Ford and do an assembly line. That would work best. So the first density is 2 grams per 1.17 milliliters. 2 grams per 1.17 milliliters. Calculate the density and compare it to this value. B is 3 grams per 1.97. 1.97 milliliters. And the last one is 5 grams per 3.14. Well, 14 milliliters. Okay, now we just calculate those values. This is 1.71 grams per milliliter. This is 3. 1.97 is 1.52 grams per milliliter. And 5 divided by 3.14 is 1.59 grams per milliliter. That's the one right there. Okay? Now the reason I said Henry Ford is repetitive sequence. Same thing over and over and over again. Talk about boredom. Being an assembly line worker. Okay, there's some more statements like those that I mentioned earlier, 1, 2, and 3, and you got to find out how many of them are true. If we had more time, we could look at those. But I don't want to eat into your lab time. Chapter 3. Alrighty. Atomic structure and periodic table. Let's see here. 120. We're going to go down to 120. The nuclear charge for an atom of fluorine. What do we mean by nuclear charge? Huh? Yeah, how many protons? Positive charge would be +9, right? +9 would be the nuclear charge. (121) The quantity A plus Z gives the number of what is A and Z? Z is equal to the number of protons, right? A is equal to the number of protons plus the number of neutrons. Okay? So if this is a neutral atom, how many electrons are there? Number of electrons equals the Z number. Right? Because it's neutral, we have to balance the charges. So if we add this one to that one, this one already includes the protons. So this number would be the number of electrons. That means what we're actually saying is the total number of subatomic particles in the atom. Protons, neutrons, and electrons. Okay? So that's why D is the best answer. All subatomic particles in an atom. Kind of a tricky question, I think. 124. Two naturally occurring isotopes exist for the hypothetical element dipium. So what's the symbol going to be? Can't use D because that means density. How about Di? There's dipium. Okay. 25% of the atoms have a relative mass of 17 AMUs. So 17 AMUs, and that's 25%. Okay. 75% have a mass of 21.3 AMUs. 21.3. Did I get that right? Yeah. And that's 75%. So what's the question? What is the atomic mass of dipium? Okay, remember how to do weighted averages. Take the fractional equivalent of this value, 0.25. Right? And multiply it by this. Take the fractional equivalent of that one and multiply it by this one. And then add them together. You got it? So what was it? 20.2? Okay. Is that everybody good with that? Okay.
It's easier to turn all percentage in decimals, right?
Percentages into decimals.
Yeah.
Oh yeah,
Oh.
yeah. Let's see, 125. It's starting to go south on me. The modern periodic table arranges the elements in order of protons, atomic number. Increasing number of protons. Yep, that's D. Now originally, Mendeleev arranged them in order of masses. Yeah, they didn't know about atomic numbers back then when he put the thing together. He was arranging them by mass and by common characteristics. So he put them in families. In fact, the first table, families were left to right. And then the second time he published it, he flipped them 90 degrees. Okay, 126. In which of the following pairs of elements are both members of the pair in the same period in the periodic table? All right, A through D. Okay, neon and magnesium. All you got to do is ask yourself, is magnesium an inert gas?
No.
No.
Either way.
Yeah. Nickel and palladium. Nickel and palladium. So we might have to look that one up. See, if there's nickel and palladium. Oh, they're in the same. There's a. Wait a minute. In the same period, right?
Same period.
Oh. Hold on a second. Hold everything. I read family. In the same period, they're in the same row.
Same row.
So magnesium and neon, no, they're not. Magnesium's in the third period, neon's in the second period. Okay. Nickel and palladium. Nickel's in the fourth and palladium's in the fifth. Okay. C. Calcium and selenium. So we find calcium is in the fourth period. Selenium's in the fourth period. Yep. That's a good one. And since we don't have any squirrely ones, potassium and rubidium are actually in the same, are alkali metals, so they're in different periods. All right, 126. 128. Yeah, 128. The correct electron configuration for chlorine. All right, so yeah, it's complete. So we start from the beginning. 1s, 2s, 2p, 3s, 3p. We'll see if we need some more after that. So s's can hold 2. P's can hold 6. How far do we go here? That's 4, 8, that's 12, so we need 5 more. That's it. Now, I know I can do that because I know the order. But if you want to use the periodic table, you say, okay, the first one, hydrogen, helium, that's 1s, 1 and 2. Then we come down to lithium, beryllium, that's 2s and 1 and 2. Then we go across to boron, boron, calcium, boron, carbon, nitrogen, oxygen, fluorine, neon. That's 2p6. Those are the P's. Right? Then we come back down to the third period, sodium and magnesium. And then we go into the 3 P's, aluminum, silicon, phosphorus, sulfur, and chlorine is 5. And you got your structure there. So you can do it from memory, or you can do it using the periodic table. Or you can use that diagonal if you want, if you memorize the diagonal thing. I don't use it anymore. But it works. Oh, we left an answer out. 129 is missing an answer. Maybe we have to do that one so I can fill in the answer. Which of the following, let me mark that one. Which of the following statements is consistent with the electron configuration over to 3p6? Okay, what can we say about that? I'm sorry?
6 electrons.
Yeah, 6 electrons in the p means it's full. And the valence shell is full. 3 is the principal quantum number, and that's the valence shell, 3s, and 3p. So if 3s is full and 3p is full, what does that mean? That means we got a noble gas. Yeah, we're all the way to the right. So that means we're all the way over to argon. That is argon. Oh, that doesn't answer the question. Okay, let's see. There are 6 electrons present in the 3p orbital. Yeah, that's right. There are 6 electrons present in the 3p subshell. Hold on a second. Shell, subshell, and orbital. So these are the principal quantum number. These are the angular momentum. Where's the magnetic quantum number, and then the angular momentum. Right, so these would be, this is where you get your S's and P's, and these are full for our example. And these are the subshells of these. So this one only has 1, this one has 3. So we have a full subshell, and we have full orbitals. Two electrons present in the 2s. No, the 2s is not a shell, it's a subshell. Right, so C is out. D says there are 2 electrons total in the second shell. No, that's wrong. So we've got to break the tie between A and B. So it's terminology is the problem. 3p orbital. 3p is not an orbital. So it has to be B. 3p subshell. So the answer here is B. Come on. There we go. Okay, that makes sense? Okay. Let me save that. All right, 131. That's getting weak too. How many unpaired electrons are present in the orbital diagram of an atom whose electronic configuration is 1s2, 2s2, and 2p4? Well, these are both paired, right? But p's can have 3 orbitals. And remember Hund's rule. We got to go 1, 2, 3, then we can go back and pair them up. So it has 2 electrons that are unpaired. Okay? $135. Okay, which of the following statements correctly describes the subatomic particle called a neutron? Let's characterize it. How about mass? Mass, approximately the same. The mass of a neutron is approximately the same as the mass of a proton. Not exactly, close. Also, it's neutral. No charge. And where does it live? In the nucleus. Okay, let's see. A says has a mass slightly less than that of a proton. No, it's slightly more than a proton. So A's wrong. B is not found in the nucleus. In an intact atom, it's in the nucleus, right? In a fission reactor or a nuclear bomb, you can have some neutrons, flying around by themselves. But for our purposes, it's in the nucleus. Has a positive charge? Nope, it's neutral. So there's no correct response out of those. Now we think that part of the reasons that the neutron is a little heavier than the proton is because it contains a beta particle, which is an electron. And in the nucleus, the neutrons and the protons exchange that beta particle. So at any one instant, you might see a beta particle transferring from a neutron to a proton, and now the proton is a neutron and the neutron is a proton. They're trying to theorize what's the glue that holds things together. We know that when you get too many protons together, there's a lot of repulsive forces. So you need something to hold them together. And we speculate that the transfer of that particle is what holds them together. Because just when that proton thinks, I'm repelled against all these other protons, it transfers a particle from a neutron, it becomes neutral and says, oh, whew, that was close. 136. Which of the following statements concerning the nucleus of an atom is correct? Okay, it accounts for almost all the mass of an atom. That's true. B, it is always positively charged. True. It contains only neutrons. False. But since there are two truths, D, more than one correct answer. (137). Which of the following collections of subatomic particles possesses a net charge of +2? Collection of subatomic particles. Alright, so A through C are unique, so we'll take those like this. What's the charge on 2 neutrons and 2 electrons? -2. 3 protons and 1 electron. 3 plus minus 1. +2. C. 3 electrons and 1 proton. 3 minuses and 1 positive. -2. So +2 is B. Let's see here, 142. Period number and group number in the periodic table are numerically equal for which of the following elements? Okay. So we got A, B, and C. A, B, and C. And aluminum, arsenic, and antimony. So we want the period number and the group number. Alright, so aluminum is period 3 and group 3. Wait a minute. It depends on how we're naming the group, numbering the groups. Yeah, that's a bad question. If we're numbering in the old system, then aluminum is 3A. It's group 3 in the representative elements. So we could say this is 3 and 3. Otherwise, aluminum would be 13. Right? 3 and 13. 13 group. So let's do that in parentheses, just in case. That's the new system. Arsenic. Arsenic is 5 and 4. Or in the new system, arsenic is 15. I think we're talking about the old system. And antimony. Antimony is 5 and 5, or 15. So, more than one correct response tells me that they're using the old system. Right? That's the only thing that makes sense. So that one needs to be reworded. Group number. So I need to insert here. Let's see, I gotta edit, excuse me. Edit. Here we go. Let's do it like this. Old group number. Okay. That, saved it. Okay, it's good. Save that. For later. 143. There's another one. Which of the following periodic table groups contains 3 or more non-metallic elements? So A, B, and C. A, B, and C. The first one is 3, 4, and 5. A. All the A's are the representative elements. Right. First 2 columns, last 6 columns. Those are all A's in the old system. Roman numeral plus an A. Let's see. Contains 3 or more non-metallic elements. Okay. If we go to 3, it's only got 1 non-metallic. That's boron. Right. So, non-metals is 1. 4 would be carbon and silicon. That's 2. 5 would be nitrogen, phosphorus, arsenic. That's 3. So C is your answer. $145. Which of the following electron configurations corresponds to an element in the same group of the periodic table as the element whose electron configuration is 1s2, 2s2, 2p5? All right, if it's in the same group as 1s2, 2s2, 2p5, if it's in the same group, it won't have the same configuration. But it will have the same configuration for the valence electrons here. So it could be, we can't go up, we go down. It would be 3s2, 3p5, or 4s2, 4p5. That would put it in the same group, where the p's have 5 in them. So we go to group, Roman numeral group 5 would be nitrogen, phosphorus, arsenic, antimony. So let's see. 3s2, 3p5, 4s2, hold on a second. There's no correct answer. Right? None of them. Have me scratching my head for a minute. All right. Let's get rid of the fog here. 146. Two unpaired electrons are present in the orbital diagram of which of the following elements? Two unpaired electrons. You're not going to get two unpaired electrons in any of the s orbitals because it's only got one s subshells. It's only got one orbital, right? It's either one unpaired or two paired. So it's got to be one with p orbitals available. So carbon has 2p2, right? Carbon 6, right? Carbon 6. 1s2, 2s2, 2p2. That means it's got like that, like that. So that has two unpaired electrons. How about neon? Neon has no unpaired electrons. Noble gases are complete. So all their electrons are paired. Magnesium. Magnesium, all of its 2p's are full. Now we're into the 3s and 3s2. So it has no unpaired electrons. Right? So the only one that fits is carbon. For that statement, two unpaired electrons. All right, there's some more of those where you have to find truth statements. How about this one? 162. Choose the correct atom that has a nuclear charge of plus 17. Right. This is trying to confuse you. If it has a nuclear charge of plus 17, it has 17 protons. You know, Z number, atomic number. The only one that fits that is chlorine. 17 protons. $169. Choose the appropriate pair of atoms that contain the same number of subatomic particles. Right, when we say subatomic particles, we mean protons, neutrons, and electrons. Okay, so A, B, C, and D. The first one is carbon 613. 613 and nitrogen 713. Let's put them all up here first. 3717 for chlorine and argon 1836. And oxygen 18. I'm checking in my head while I'm doing these to see if they're even written correctly. 19, excuse me. And the last one, lithium, 3,6, and lithium, 3,7. Okay, you can start from the top or the bottom, either one. Subatomic particles. This one has protons and neutrons already added. So we just add 6 together for the electrons and we get 19. 19. And 7 plus 13 is 20. So that's not it. 17 plus 37 is 54. Right? And 18 plus 36 is 54. Right? So that's a good answer. That's the only answer, actually. If we added the rest of them up, we get a different value here. 26 and 28. And this would be 9 and 10. Do I see why I'm doing that? Okay. So B is our answer. I'm sorry?
The subatomical particles, you just add the number.
Recognizing that for the neutral atom, the Z number is also the number of electrons. Right? So the atomic number is the number of electrons in a neutral atom, and the A number already contains the protons, neutrons and protons. So we just add the Z to the A, and that gives us everything. $175. Choose an appropriate pair of elements that are in the same period of the periodic table. The same period. All right? A through D. So, rubidium and strontium. Yeah, they're right next door in the 5th period. Alkaline metal, alkaline earth. Right? So that one works. Oh, we found our answer. Because there are no squirrely ones in there. Right? Nitrogen and lead are in 2 different periods. Fluorine and chlorine are in the same group, but not the same period. Molybdenum and rhenium. Molybdenum. It's in the 5th period. And rhenium is in the RE. Where is rhenium? I'm looking straight at it and don't see it. Oh, there it is. Yeah, rhenium's in the 6th period. Molybdenum's in the 5th period. Yep. Lots of examples there. We're just hitting 1 or 2 of them. Oh, in fact, we're done. Now, while we were doing all this, did anything else come to mind that you needed to work on?
Oh, yeah.
Okay.
I'm good, though, but I need to work on it.
Oh, you need to work on it.
Yeah.
Okay. Anything I can help you with right now is a good time.
The 1s, 2s, like that, what is the difference between the shells, the subshells, and the orbital? I don't know which is which.
Oh, the principal quantum number, and then the, I get these confused. I think this is the magnetic, no, this is the angular momentum quantum number. Then the magnetic quantum number, and then the spin. Okay, so these represent the shell, principal quantum number. These are a subshell because they're derived from the shell. We know a number for the shell, 1, 2, 3, 4, and then the subshell is derived from each one of these. So if we went to this one, it would be 0, 1, and 2 possibilities. Subshell. And then for each one of these, we have an orbital. And it's derived from these. If we use 2, then it'd be -2, -1, 0, +1, +2. So they're derived from each other. Okay. Let me scroll back to the top. Long way to go. And it's already been saved, that's good.
Could you explain dimensional analysis?
Dimensional analysis?
Yes.
Yeah.
You break it down like really small increments,
Okay.
because I'm a little lost on that.
When you hear dimensional analysis, think conversion factors. In other words, you're converting from one unit of measure to another unit of measure. And usually the way we do that, in fact, the only way I've ever thought of is is with quotients of some kind. So you have maybe grams, so many grams per milliliter would function as a conversion factor. You start off someplace like miles. Let's say 100 miles. And then you want to end up with kilometers. Okay, how do you get there? You got to convert miles to kilometers. So if you know the conversion factor from miles to kilometers, notice that the miles is in the denominator so that we can cancel. And then the numerator contains the unit we want. If you know that value, then you can do it in one step. If you don't, then you might have to chain them together. Let's see. I could be, this is ridiculous, but I could go miles to feet. Okay. Then I could go feet to inches. Okay. And then I can make my transition to metric system because I know this conversion factor. Inches, centimeters. 2.54 centimeters.
So do you always start out with the biggest measure unit and then break it down to the smaller?
No.
As you go across?
No, you just start with what you're given. And then the question will tell you where you're going to end up. They're not always bigger than and smaller. Now that we're in centimeters, we can say how many centimeters in a meter? 100, right? And now we can go to meters, kilometers. 1,000 meters in a kilometer. And then that's a chained conversion. Now that we've done all the thinking, we could just crunch numbers. 100 times 5,280 times 12 times 2.54 divided by 100 divided by 1,000. Got your answer. I don't know, did that help any? Or did you want more theoretical?
Yeah, like can you do it with the molecules and atoms, like an example of that?
Sure. Mm-hmm. Let's say we're given something simple. Like we're given, all right, we'll start off really simple. Like we're given 25 molecules of water. And we want to know how many atoms that is. Okay? So we need a conversion factor that will go from molecules to atoms. Can we find one that does that? Well, how many atoms in the molecule of water? Two plus one is 3. 3 atoms in one molecule. So 3 times, that cancels here. This is the unit we want. So 3 times 25 is 75. So that many molecules is that many atoms. Now, if we want to make it, let's modify that. Say we have 25 moles of water. Now we want to know how many atoms. We need a different conversion factor. Moles to molecules, right? 6.022 times 10 to the 23rd molecules per mole. That's Avogadro's number. Now we got the moles converted. Now we take molecules and go to atoms. So now we can say, like we did before, molecules to atoms, and that's 3 atoms per molecule. So now we have another chain conversion. 25 times Avogadro's number times 3 and divided by 1.
Okay, that makes sense.
Yeah.
You only use Avogadro's number when you're doing mole, right?
That's what it's equal to. 1 mole is Avogadro's number. Yep. And all conversion factors start off as an equivalence. If you say 1 inch equals 2.54 centimeters, you make a conversion factor out of it. You just ratio the two.